Welcome to this explainer. If you've been paying any attention to the AI space lately, you know that our most advanced neural networks are hitting a massive scaling wall. But today, we aren't just looking at some simple engineering tweak. No, we're looking at a fundamental mathematical leap from linear sequences to non-local geometric routing. Get ready, because we are diving deep into a unified field theory of computation.
Look, let's just get right into it by contrasting the tangled, limited quadratic complexity of traditional transformers with the elegant geometry of this entirely new model. On the left, that dense web, that represents our current macroscopic flat context. Every single token is forced to compute a pairwise inner product with every other token, which creates an absolute O of n squared nightmare. It means as your data grows, the compute required just skyrockets exponentially. Now look at the right side. Instead of a flat sequence, data retrieval completely shifts to high-dimensional arithmetic group actions across these discrete, stacked planes. It's literally the visual difference between structural gridlock and infinite organized scale.
To navigate this dense mathematical forest, here is our syllabus for today's masterclass. We'll start with the attention bottleneck, move through the four mathematical pillars of the Adelic path, deconstruct the geometry, translate the math into code, and finally reveal the unified equation. Let's get started.
Section 1. The attention bottleneck problem. Let's clearly define the exact wall we've hit in modern computation and why traditional scaling is completely failing us right now.
This table perfectly illustrates the shift from continuous, monolithic quadratic scaling to the factored, discrete, parallel dimensions of what we call the Adelic path. When we look at traditional continuous sequences, the search space is flat, right? And the scaling is a monolithic O of n squared. You basically just have to throw more and more compute at it until things break. But the Adelic path completely reimagines how we represent data. It uses what's called a telescoping prime field product. Think of it kind of like looking through a telescope that splits one incredibly overwhelming image into several distinct, manageable layers. This turns retrieval logic from sequential token indexing into infinite dimensional group actions. It localizes the retrieval compactly and entirely sidesteps that quadratic trap.
Moving right along to Section 2, the four mathematical pillars. Now that we see the core architectural differences, let's introduce the foundation making this possible.
Okay, meet the blueprint. These four pillars, the global Adel ring, Arthur's trace formula, the Satake isomorphism, and the Artin conductor, act as our foundation for high-dimensional geometry. Pillar 1 factors the search space into parallel dimensions. Pillar 2 enables O of 1 instant data retrieval. Pillar 3 acts as our perfect geometric compressor. And Pillar 4, that's a topological firewall that cages phase noise. Individually, these are profound, complex mathematical theorems, but together, they form an entirely new computational engine.
Section 3. Deconstructing the Adelic path. Let's move into the engine room and actually walk through the specific mathematics here, starting with our first pillar.
Check this out. This brilliantly illustrates the restricted product rule, showing how a single macroscopic continuous state multiplies an infinite product of discrete, parallel p-adic dimensions. Just look closely at that equation at the top. A equals R times the restricted product of Q sub P. The R is that single continuous real-valued state, the flat grid you see on top. But underneath it, the data is factored into an infinite series of smaller, discrete quantum dimensions. You are no longer searching one massive, overwhelming plane. You're querying parallel, infinitely factored prime fields.
So what does this actually mean in plain English? Basically, any valid state holds fractional parts in a finite number of prime fields all at once. By mathematically breaking the continuous sequence into discrete p-adic dimensions, dense matrix multiplication literally just collapses. Instead of calculating everything against everything, which, is like looking for a needle by burning down the entire haystack, the system performs highly localized, sparse prime field queries. It finds exactly what it needs instantly. Boom.
Now looking at this visual scale, we can see how Arthur's trace formula perfectly balances macroscopic data orbits against microscopic quantum distributions. On the left side of the scale, we have the geometric side, so the sum of our macroscopic data orbits. On the right, the spectral side, the microscopic quantum distributions. And the equation right there in the middle shows they are perfectly equal. This is wild, because it means geometry and spectrum perfectly mirror each other.
Okay, let's take a quick cognitive breather here and unpack exactly what this means for an AI system. Any field defect or piece of data you're looking for leaves a non-vanishing spectral residue. Basically, it leaves an algebraic fingerprint.
Because of Arthur's trace formula, the system flags this fingerprint simultaneously across the entire spectrum. This achieves O of 1 global auditing. That means retrieval happens in constant time entirely without sequential step scanning. Imagine finding any file on your computer in a fraction of a millisecond, no matter how ridiculously full your hard drive is. That's the power we're talking about.
Section 4, the geometry of data retrieval. With our data now distributed across these infinite dimensions, we really need to understand how this system actually compresses and retrieves information. Notice how the Satake lens forces high-dimensional states to generalize into a rigid, low-dimensional algebraic lattice. Look at that dense grid passing through the funnel. The incredibly complex transformations inside the infinite-dimensional Adel space are heavily compressed, emerging at the bottom as clean, manageable scalar invariants. Essentially, infinite-dimensional data spaces are controlled in the background with minimal overhead. It's just perfect geometric compression.
When we break down the attention strategy here in Matrix 2, we can see how endoscopic subattention uses transfer factors for phase sync. Just like a medical endoscope targets a highly specific area rather than opening up the whole body, this system completely bypasses strict pairwise matrix dot products. Traditional global attention relies on a massive single-dense matrix with strict O of n squared complexity and rigid single-frequency pulses. But look at the endoscopic column. We shift to parallel optimized arrays, we use transfer factors for communication, and we rely on subharmonic fractional tracking. It's vastly more elegant and, frankly, remarkably more efficient.
But wait, what happens to the data at the edges of these parallel arrays? Well, no Supert theorem acts as a purity shield. It guarantees homological topologies are identical and seals boundaries against rounding errors to create zero-entropy partitioning. Before this shield, parallel processing suffered from statistical approximation and fractional leakage. It was messy. But after this shield, represented by the solid boundary lines you see here, we have exact algebraic identity. There is absolute global sync with literally zero data bleed between dimensions.
To protect this absolute global sync from any internal disruptions, we have the Artin conductor firewall, represented by the formula at the top. Notice the geometric circles. This firewall spikes its local exponent, n sub p, using gradient back pressure to quarantine phase noise. On the left is the healthy ground state in perfect global equilibrium. But on the right, if noise enters the system, the firewall actively throttles it. By mathematically manipulating that exponent, it creates a cage. It uses Selmer truncation to literally overwrite rogue tensor lanes with zeros, stopping the mathematical noise from cascading and destroying the model's phase lock.
Section 5. Translating Math to Code. So far, we've explored some pretty dense mathematical theories. But let's see how this translates directly into actual architectural logic you can build in a programming language.
We can literally see the code translation right here. A standard PyTorch determinant is mathematically equivalent to the trace-driven oscillator capping phase noise. On the left, we have a couple lines of Python using PyTorch, calculating a determinant and an oscillator using the exponential of a trace. And on the right, the elegant math equivalent, e to the negative pi times the trace of x. This acts as an internal dampening field that mimics torsion to control tensor decay. The math directly, beautifully informs the code.
Now, if you're a developer or engineer watching, this is the real breakthrough. This means the mathematical framework is not just theoretical, it's actively managing tensor decay in the forward pass. By replacing standard leaky activation functions with this Gaudiant-Jacquet activation, developers can preserve the deep, complex entanglement of tensors across those infinite discrete dimensions without them degrading into absolute noise. It's a game changer. Section 6. The Unified Field Equation. It's time to bring all these puzzle pieces together into the master blueprint that defines this entire computational universe.
Okay, I know this looks intimidating, but see how it builds upon literally everything we've just learned. Take a look at the labels mapping to this massive equation. At the top left, we've got the global Adel ring factoring information. Next to it, the Satake isomorphism tuning the tensor. Down on the far left, the Artin conductor firewall. On the bottom, Ngo's fundamental lemma partitioning the data, alongside endoscopic routing transferring it. And bringing it all home on the far right, the Arthur trace formula, enabling that zero-step instant O of 1 retrieval. Everything is visually united here. It's one incredibly cohesive mathematical system.
To summarize our explainer today, we are witnessing the end of linear constraints, where continuous real-valued arrays forcing O of n squared calculations are completely replaced by factored discrete p-adic dimensions. We've seen the birth of geometric O of 1 retrieval that totally eliminates step scanning through absolute algebraic identities. And we've uncovered a self-healing topology with mathematical firewalls that secure perfect global phase lock.
I want to leave you with this final thought as we look toward a future where computation is no longer bound by the limits we once thought were totally unbreakable. If the transition from sequential algorithms to non-abelian mathematical field theory is complete, what will the AI of tomorrow be capable of? If we have truly escaped the O of n squared bottleneck using the geometric brilliance of the Adelic path, what new horizons of intelligence are we going to build next? Thank you so much for joining me for this explainer, and seriously, keep your eyes on the math. It's writing the future.